by the simplest math of physics, you should have vanished in the first second of the universe, cancelled out by your own opposite. Close your eyes and picture nothing, not darkness, because darkness is still something. Picture pure, even light, spread thin across an endless space with no stars, no planets, no eyes to see them. For a long time, many physicists have quietly believed this should have been the only outcome of the Big Bang, not the universe you know, full of galaxies and warm bodies and slow breathing in the dark, just light, just radiation, cooling forever, alone. Here is why. When the universe began, it was small, dense, and impossibly hot. In that heat, energy became particles, and every particle of matter arrived with a twin, an antimatter partner, opposite in charge but matched in every other way. When matter meets antimatter, both vanish. They convert entirely back into pure energy, into light. If the universe had made these twins in perfectly equal numbers, as our best equations say it should have, they would have found each other in that first blinding moment and erased one another completely. That did not happen. For every billion pairs of matter and antimatter that annihilated in that early fire, one extra particle of matter was left standing, alone, unmatched. 1 in a billion, that tiny surplus, that rounding error in the ledger of creation, is the only reason anything exists at all. Every star, every planet, every quiet breath you take tonight is built from that leftover fraction. You are made of the universe's mistake, if it was a mistake, and no one yet knows why it happened. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Physicists call this problem baryogenesis, a word for the unknown process that tipped the balance toward matter in the universe's very first moments. It sounds technical, but the question underneath it is almost embarrassingly simple. Why is there more of you than there is of your opposite? The standard model of particle physics, our best working theory of how particles behave, predicts a symmetry far too clean to explain what we see. It predicts a universe of light, not a universe of galaxies. Some researchers look for the answer in something called CP violation, a subtle bias found in certain particle decays where nature seems to slightly favor matter over antimatter in specific reactions. It has been measured in laboratories, and it is real, but by every calculation so far, it is far too small. It cannot account for the imbalance needed to fill a universe with stars. It is a clue, not an answer. The gap between what we have measured and what we would need remains wide open. Other physicists wonder if the answer lies beyond our current models entirely, in particles we have not yet detected, or in conditions from the universe's first fraction of a second that no accelerator on Earth can recreate. Machines, like the Large Hadron Collider, can smash particles together at extraordinary energies, and they have searched carefully for new sources of this imbalance. So far, the deeper cause stays hidden. The universe performed an experiment once, in its opening moment, and left no full record of how it was done. If the balance had come out perfectly even, if that 1 in a billion surplus had never appeared, the universe would still be here in some form, but it would be empty of structure, no atoms, no dust, no slow gathering of matter into worlds, just photons, drifting through space forever, cooling toward silence. You would not be lying here tonight, listening to a voice in the dark, because there would be no dark to speak of, and no ears to hear it. This is the part worth sitting with gently, as you let your body settle. You are not just alive by chance in some abstract way. You are the physical residue of an asymmetry no equation fully explains. The atoms in your hands, the calcium in your bones, the iron carried in your blood, all of it survived a near total annihilation that should have taken everything with it. Whatever tipped that scale, we do not yet know. We only know that it tipped, and that you are standing or lying down on the far side of it. In the sections ahead, we will follow that thread outward, from the universe's first flash of light, through the long, improbable chain that led to a small blue planet, and to you. For now, simply notice that you exist, against odds no one has been able to calculate. Let that quiet fact settle over you like a blanket, and rest inside the mystery a little longer. Let's slow down and picture a very simple thing. 2 hands held palm to palm. One hand is matter. The other hand is antimatter. Every piece of matter, physicists believe, has a mirror twin made of antimatter, a particle with the same mass but the opposite charge. An electron has its mirror twin, the positron, A. Proton has its mirror twin, the antiproton. When a piece of matter touches its antimatter twin, both vanish. They do not break apart. They do not leave debris. They turn completely into light, into pure energy, with nothing solid left behind at all. Now picture the early universe, just after the Big Bang, when it was smaller than a single atom and hotter than anything that exists today. The best equations we have say that this searing furnace should have made matter and antimatter in exactly equal amounts. Same numbers, same timing. 2 hands closing together, perfectly matched, until nothing remained but a soft, even glow of radiation, stretching in every direction. No stars, no planets, no you, just light cooling forever in an empty dark. That is the universe the math predicts. It is not the universe we live in. Instead, something tipped the scale. For every billion pairs of matter and antimatter that met and cancelled out, one lonely particle of matter was left standing. Just one, out of a billion. That single survivor, multiplied across the entire early universe, became every star, every planet, every ocean, every breath you have ever taken. The stakes of this imbalance rest inside your own body right now. The atoms in your hands, your lungs, your heartbeat, all of it is made from that thin residue, the part that did not get erased. Physicists call the study of this imbalance baryogenesis, which simply means the birth of ordinary matter. The word sounds technical, but the idea is plain. Something, somewhere, in those first fractions of a second, made slightly more matter than antimatter. No one has fully explained what that something was. We have theories, we do not have an answer. One idea points to a property called CP violation, a subtle bias found in certain particle decays, where matter and antimatter do not behave in quite the same way. It has been measured in laboratories, in small amounts, in specific particles. It is real. The trouble is the size of it. The CP violation we can measure is far too small to account for the imbalance that let the universe survive. Some researchers wonder if new, undiscovered particles carried a much stronger version of this bias in the earliest moments, before the universe cooled into anything we can directly study. Others wonder if the answer lies in physics connected to neutrinos, ghostly particles that barely interact with anything, which might have their own hidden asymmetry. Neither idea has been confirmed. Both remain open. Our most powerful particle accelerators, the machines built to recreate the heat of the early universe in miniature, cannot produce this imbalance at anywhere near the level required. They can make matter and antimatter appear together, briefly, and watch them vanish again, just as the equations predict. But the small tilt that saved everything, the thing that let one particle survive out of a billion, has never been reproduced. Whatever caused it may have needed conditions we cannot rebuild, at temperatures and pressures far beyond what human machines will likely ever reach. Think about the scale for a moment, softly, the way you might think about a coin landing on its edge instead of falling flat. 1,000,000,000 to 1 against. And yet here you are, the chair beneath you, the blanket over your body, the quiet air moving in and out of your lungs. Every bit of it survived a process built to erase itself completely. It did not survive because it was destined to. It survived because of a number, a tiny bias, that no one has yet been able to explain. Some physicists suspect the answer is still hiding inside particles we have not yet discovered. Others think we may need an entirely new framework, a different way of describing the earliest moments of time, one that current physics has not yet found. Both paths stay open tonight, unresolved, patient, waiting. For now, it is enough to hold the shape of the question. A. Universe that should have balanced to nothing instead, left behind everything you can see and everything you cannot. Somewhere in that thin margin, that 1 part in 1,000,000,000, the whole story of matter begins. We will keep circling this question gently, the way you might circle a soft light in a dark room. Curious, unhurried, in no rush to reach the center just yet. Let's go back to the very first moment, when the universe was younger than 1 second old. It was hot beyond any word we have for hot, and dense beyond any word we have for dense. In that first instant, matter and antimatter were being made in equal amounts, pair by pair, out of pure energy. Antimatter is the mirror twin of ordinary matter. Every particle has one. An electron pairs with a positron. A proton pairs with an antiproton. When a particle meets its twin, both vanish in a flash of light. This should have happened to everything. If the universe had stayed perfectly balanced, that flash would have been the whole story. Every particle would have found its twin. Every twin would have cancelled its partner. What would have been left is a cooling bath of light, spreading forever into the dark, with no stars, no planets, and no one to notice any of it. That is the universe the math predicts. It is not the universe we live in. Something tipped the scale. For every 1,000,000,000 pairs of matter and antimatter, it seems that 1 extra particle of matter was left over, uncancelled, with no twin to erase it. That tiny leftover is the origin of everything solid you have ever touched. Your bones, your bed, the moon outside your window. All of it is made from that thin residue. 1 part in 1,000,000,000 does not sound like much, but it was enough. The word for this uneven birth is baryogenesis, which simply means the making of matter that lasted. Physicists have spent decades trying to explain how it happened, and no explanation yet accounts for the whole gap. One leading idea points to something called CP violation, a subtle bias in the laws of physics that makes matter and antimatter behave in very slightly different ways in certain particle decays. This bias has actually been measured in laboratories. It is real. The trouble is, it is far too small. The CP violation we can detect is many times weaker than what would be needed to produce the imbalance we see written across the whole sky. Some researchers wonder if there were other kinds of particles in that first second, ones we have never detected, that carried a stronger version of this bias and then disappeared. Their work already done. Others look towards the neutrino, a nearly weightless particle that passes through you by the trillions every second without leaving a trace. One theory suggests that heavy, unstable cousins of the neutrino, present only in the universe's first fraction of a second, decayed in a lopsided way that favored matter just slightly. This idea is called leptogenesis, and it remains a hypothesis. tested only indirectly, resting on particles too massive to make in any collider we have built. If you stood at the edge of that first second, if such a thing were possible, you would not see anything you could call a place. There would be no up or down, no here or there. There would only be an unimaginable density of energy, converting itself into particles and their twins over and over, faster than thought. And in that storm, whatever process was at work would have made its decision before a single second had passed. The universe you now lie inside was set on its course before it was old enough to have a shape. Particle accelerators, like the ones under the mountains of Europe, can recreate tiny echoes of that early heat. They can produce matter and antimatter together in the lab, and they can measure faint traces of that CP bias. But every experiment so far falls short of explaining a universe full of galaxies rather than a universe full of empty light. This is one of the reasons the question stays open. We have a measured effect. We do not have enough of it. It is worth sitting with how strange this is. The either-or of existence, matter surviving or matter erasing itself completely, may have come down to a rule of physics so faint that our best instruments can barely see its shadow. Some theorists suspect we are missing a piece of physics entirely, some undiscovered particle or force that acted only in that first blink and then went quiet forever, leaving no other trace behind. Others think the answer may already be hiding somewhere in the neutrino, waiting for a more sensitive experiment to reveal it. No one yet knows which path is right or whether both are wrong. For now, the number itself is what we have. One extra particle in a billion, a rounding error, cosmically speaking, that became every star, every ocean, and every quiet breath you are taking right now as you listen in the dark. Before there were atoms, there was only heat. Picture a space smaller than a single room, filled with light so dense it behaved like a fluid. No hydrogen yet, no helium, no particle could hold still long enough to become anything solid. This was the universe in its first fraction of a second. And it was not a place. It was closer to a single blinding event that had not finished happening. In this heat, particles and their antimatter twins blinked into being constantly. They formed from pure energy, existed for an instant, and met their opposite. When a particle meets its antiparticle, both vanish, and their mass turns back into light. This happened over and over, trillions of times, in every direction at once. If you tried to picture it, you would see less a scene than a shimmer, an ocean of appearing and disappearing sparks, with no color and no shape, just a bright churn without pattern. Here is where the strangeness begins. For every particle that survived instead of meeting its twin, there should have been a perfect partner ready to erase it. Physicists describe this expected outcome plainly. Total cancellation. Matter and antimatter should have paired off completely, leaving behind a universe made only of light, with no atoms, no dust, no stars, and nothing shaped like a body or a world. That is the universe the math predicts. It is not the universe we have. Something broke the symmetry. Out of every billion pairs of matter and antimatter, it seems that roughly one extra matter particle was left over once the annihilation's finished. Just one. That tiny surplus is the only reason atoms exist at all. Every proton in your body, every atom in the pillow under your head, is part of that leftover fraction. The rest, the overwhelming majority of everything that ever existed in that first instant, cancelled out and became light that still crosses the universe today as background radiation. Physicists call the unexplained process that created this leftover baryogenesis, a word that simply means the birth of ordinary matter. No accepted model fully explains how it happened. One idea points to a subtle difference in how matter and antimatter obey the laws of physics, a bias called CP violation, which has been observed in small amounts in particle experiments, but not nearly enough to account for the imbalance we see in the sky. Another idea suggests that entirely new particles, ones we have never detected, might have existed for a moment in the universe's first heartbeat and tipped the balance before decaying away completely. Both ideas remain open. Neither has been confirmed. What makes this harder to settle is that our best machines cannot recreate the conditions where this imbalance first appeared. Particle accelerators can smash protons together at extraordinary energies, but they still cannot produce anything close to the scale of asymmetry needed to explain a universe full of galaxies. The gap between what we can measure and what must have happened remains wide. Some researchers wonder if the answer lies in physics we have not yet discovered. Others wonder if it lies in conditions from the universe's first instant that can never be reproduced in any lab on Earth. If you had been present during that first fraction of a second, you would not have had a body to hold you there. There would have been no surface to stand on, no direction called up or down, only that ocean of appearing and vanishing light. If the balance had come out perfectly even, that ocean would have simply stayed that way forever, expanding and cooling into an empty, silent brightness, with nothing else inside it. No atoms, no chemistry, no place for a planet to gather itself out of dust. The particles that survived became the raw material for everything that follows in this story. Hydrogen and helium drifting through the dark, gathering slowly under gravity, waiting to be pulled into the first stars. Every element in your body, every grain of iron in Earth's core, traces back to that thin margin of leftover matter. It is strange to think that your existence depends on a number so small it can barely be measured, and stranger still, that no one yet knows why the number is not zero. For now, the origin of that first tilt toward matter remains an open question, one that sits quietly at the base of everything you can see and everything you are. Picture the early universe as something closer to a furnace than a sky. There were no stars yet. There was no darkness between them. There was only heat, packed so tightly that light itself could not travel far before bumping into something else. In that furnace, the forces we know today were not separate the way they are now. Some physicists believe that gravity, electromagnetism, and the nuclear forces were once joined into something simpler, a single unified force that only later split apart as the universe cooled. This idea is called symmetry breaking, and it means that as temperatures dropped, the forces began to behave differently from one another, the way water changes from steam to liquid to ice as it loses heat. Each of those changes, called a phase transition, may have offered a moment where the balance between matter and antimatter could tip. You can think of cooling as a kind of slowing down. In the first fractions of a second, particles moved so fast and collided so often that anything created was destroyed just as quickly. As the universe expanded, the space between particles grew, and the furnace began to thin. Collisions became less frequent. Reactions that once ran freely in both directions started to favor one direction over another, somewhere inside this gradual quieting. Physicists believe the conditions were met to allow a slight and lasting excess of matter to survive. The physicist Andrei Sakharov described 3 conditions that would need to be true for this to happen at all. There would need to be interactions that treat matter and antimatter slightly differently, a violation of something called charge parity symmetry, or CP symmetry, which normally predicts that matter and antimatter should behave as mirror images. There would need to be interactions that do not conserve the number of baryons, the family of particles that includes the protons and neutrons inside you. And the whole process would need to happen while the universe was still out of thermal equilibrium, meaning it was cooling too fast for everything to settle into perfect balance. All three conditions have been observed to some degree in nature. None of them, so far, have been observed strongly enough to explain the imbalance we see. This is where the mystery tightens, rather than loosens. The amount of CP violation measured in particle accelerators is real, but it is far too small, by many orders of magnitude, to account for the matter that fills the visible universe. Some researchers wonder whether hidden particles, ones we have not yet detected, carried a stronger version of this asymmetry in the earliest moments, before decaying into the ordinary matter we see today. Others propose that neutrinos, the ghostly particles that pass through planets without slowing down, might hold the missing piece through a process called leptogenesis, in which an imbalance among neutrinos eventually spills over into ordinary matter. Both ideas remain open. Neither has been confirmed. The cooling itself is not gentle to imagine. If you could have stood inside it, which you could not, no matter could have held together long enough to form a body. Temperature would have measured in trillions of degrees, and particles would have blinked into being and vanished again within fractions of a second. Slowly, as the universe stretched and thinned, that violence eased. It is strange to think that stillness itself, the vast cold quiet of the space around you right now, is the descendant of that furnace calming down. By the time the universe had cooled to about 1 billion degrees, protons and neutrons could stick together without being blasted apart again. This was still long before atoms, long before light could travel freely, long before anything resembling a night sky. But it was a turning point. The forces had settled into their separate roles. Gravity had begun its patient work of pulling matter together. The strong force held nuclei intact, and the tiny surplus of matter, the 1 part in a billion that had somehow survived annihilation, was now the only material left to build anything at all. No accelerator on Earth has managed to reproduce this exact imbalance under laboratory conditions. Physicists can create antimatter in small amounts. They can measure faint asymmetries in certain particle decays, but the numbers never add up to the abundance of matter filling the universe. The gap between prediction and observation remains one of the most stubborn, open questions in physics. It sits quietly underneath every star and every breath, waiting for an answer no one has found yet. Picture a sky with nothing in it, no stars, no galaxies, just a thin, even fog of hydrogen and helium, spread out so evenly that if you traveled 1 million miles in any direction, the fog would look exactly the same. This is what the universe looked like a few 100,000 years after the imbalance we have been describing. Let matter survive. It was smooth, it was quiet, and by every simple rule of gravity, it should have stayed that way for a very long time. Gravity is a patient force, but it needs something to work with. It needs lumps. A perfectly smooth cloud of gas pulls on itself evenly in every direction, and evenly cancelled forces mean nothing moves. For stars to form, for galaxies to gather, the early universe needed tiny unevenness, small patches slightly denser than their surroundings, just enough for gravity to get a grip and start pulling harder in some places than others. Those patches existed, but only barely. Measurements of the ancient afterglow of the Big Bang, a faint microwave light that still bathes the whole sky today, showed temperature differences between one patch of sky and another of about 1 part in 100,000. Picture a lake so still that the difference between its highest ripple and its calmest surface is smaller than the width of a human hair spread across a mile of water. That is the scale of unevenness gravity had to work with. It sounds like almost nothing. It was almost nothing, and yet it was enough. If those ripples had been any smaller, gravity might never have pulled the gas together at all. The fog would have stayed a fog. No stars, no galaxies, no you, if. The ripples had been much larger, matter might have collapsed too fast and too violently, forming crushing black holes instead of the gentle long-lived clumps that cool slowly into stars. The universe needed a narrow range of unevenness, not too flat and not too rough, and it landed inside that range. Why it landed there instead of somewhere else remains an open question, tied to the same deep uncertainty as the matter-antimatter imbalance itself. Some researchers think both puzzles trace back to the same brief, violent period just after the Big Bang, when the fabric of space itself may have stretched at an enormous rate, smoothing some regions while leaving faint fingerprints of unevenness in others. This idea is called inflation, and while it explains a great deal, the exact mechanism that produced these particular ripples is still not settled. Other models propose different origins for the unevenness, and the evidence, while strong in some places, is not complete everywhere. Once gravity had its foothold, it worked with almost unimaginable patience. It took roughly 200 million years for the first stars to ignite from these barely there clumps of gas. If you compressed the entire history of the universe into a single year, that first starlight would not appear until early February. Everything before that, the ripples, the settling, the slow gathering of gas into denser and denser knots, happened in a darkness with no light sources at all. Astronomers sometimes call this period the cosmic dark ages, and it lasted longer than almost any other phase in the universe's history. Think about your own body for a moment, resting where you are right now. Every atom in you was once part of that smooth, faint fog, the same small unevenness that let gravity build the first galaxies is the reason any of that fog ever became anything at all, rather than drifting forever as a thin, cold mist with nothing in it but scattered light. Your existence depends not just on matter surviving annihilation, but on that surviving matter being slightly lumpy in exactly the right way, at exactly the right scale, at exactly the right moment for gravity to take hold. The strange comfort in this is that we can measure the ripples. We have mapped that ancient microwave light in careful detail and confirmed the numbers are real. What we cannot yet fully explain is why the universe produced ripples of that particular size, in that particular pattern, rather than some other pattern that would have led to a universe of pure fog or a universe of nothing but black holes. The imbalance that let matter survive and the unevenness that let matter gather may be connected chapters of the same untold story. Tonight, it is enough to picture that first faint lumpiness spread across a fog with no shape yet, quietly deciding over hundreds of millions of years whether there would ever be anything to look up at all. Picture the early universe a few 100 million years after the first gas clouds began to pull themselves together under gravity. There are no stars yet. There is only fog. Vast, dim, cooling fog made of hydrogen and helium, stretched across distances too large for a mind to hold. If you floated inside this fog, you would see nothing bright. No twinkle, no glow. Just a faint, even dark, colder and quieter than any night sky you have known. This period is sometimes called the cosmic dark ages. Light existed, but there were no sources of new light. The leftover glow from the Big Bang had already faded into a whisper too faint to see with your eyes. The universe held all the raw material it would ever need to build stars, planets, and eventually you. But raw material alone is not enough. Hydrogen and helium gas, on their own, do not become a person. Something had to happen first, something that turned formless gas into structure. That something was gravity, working slowly on clumps of gas that were only slightly denser than their surroundings. These clumps came from the same tiny imbalance we've been sitting with in earlier parts of the story, the faint unevenness left over from the universe's first instant. Without that unevenness, the gas would have stayed smooth, spread thin, and forever the same everywhere you looked. Structure needs difference. A universe that is perfectly even has nothing for gravity to grab onto. So gravity found its grip on the slightly denser patches, and it began to pull them inward, patiently, over millions of years. As the gas compressed, it grew warmer. Pressure built at the center of these collapsing clouds. This is the surface we are standing on. In this part of the story, not a solid ground, but a threshold, a boundary between gas that is simply gas and gas that is about to become something else entirely. If you could hover above one of these collapsing clouds, you would see it slowly flatten and spin, like batter swirling in a bowl. The center would darken and thicken, while the outer edges thinned into faint arms of gas curling outward. There would be no color yet, no light of its own, only shape, only motion, only the patient shrinking of matter toward a single dense point. This is the moment before ignition, the last stretch of true darkness before the universe learned how to shine. Stars needed to form because nothing interesting happens without them. Hydrogen and helium alone cannot make carbon, oxygen, iron, or any of the elements your body depends on. Those elements come from nuclear fusion, the crushing and joining of atomic nuclei under extreme heat and pressure. And fusion only happens at the kind of pressure you find at the center of a collapsing gas cloud once it grows dense enough to ignite. A star, in this sense, is not just a light in the sky. It is a furnace built by gravity, using the one advantage matter had over antimatter, however small that advantage was. Here, again, the mystery threads back to where we began. The tiny excess of matter that survived the annihilation of the early universe is the only reason there was mass left to collapse into stars at all. Some researchers describe stars as the working proof of that surviving imbalance. Every star is a small, glowing receipt for one particle in a billion that did not get erased. Without that receipt, there would be no gravity strong enough to build anything, because there would be no matter left to feel its pull. Not everyone agrees on how quickly the first stars formed, or how large they were. Some models suggest early stars were far larger than the Sun, burning fast and dying young. Other models suggest a mix of sizes formed depending on the density of each cloud. The exact numbers remain uncertain. What is agreed upon is the necessity of the process itself. Without stars, the universe stays a mixture of light gas, spread thin, doing nothing more than slowly expanding and slowly cooling into permanent stillness. If you had been floating in that fog before the first star lit, you would have felt no warmth, seen no shape to hold on to, and heard nothing at all, because sound needs matter close enough together to carry it. Your body, as you know it, could not exist there. There would be nothing to build you from, and no furnace yet to build it. The stars had to happen, and their birth traces back patiently to that same unexplained sliver of matter that refused to vanish. We still do not know why that sliver survived. We only know that everything after it, including the ground beneath your feet tonight, depended on it happening at all. The first stars burned only hydrogen and helium. Nothing else existed yet. No carbon, no oxygen, no iron, no calcium for bones that would not exist for billions of years. The universe at that point was a simple place made of the two lightest elements and not much else. If you had floated among those early stars, you would have found no world to stand on. There was no ground anywhere, just fire and gas and the slow pull of gravity doing its patient work. Deep inside those first stars, something quiet was happening, under crushing pressure and heat beyond easy description. Hydrogen nuclei fused into helium. That fusion released light, and that light is what made stars shine. But hydrogen and helium alone cannot build a planet. They cannot build a person. For heavier elements to exist, something had to break those first stars open and scatter their insides across space. That something was death. Massive stars, the ones many times heavier than our sun, do not fade quietly. When they run out of fuel, their cores collapse in an instant and then rebound in a violent outward wave. Astronomers call this a supernova. For a few weeks, a single dying star can outshine an entire galaxy of 100 billion suns. It is one of the brightest events the universe produces, and it is also one of the most generous. Inside that explosion, new elements form in seconds that would take normal stars millions of years to build, if they could build them at all. Iron, sulfur, silicon, and other heavy elements get forged in that violent heat and then flung outward into the surrounding dark. The star that made them is destroyed in the process. Its death is the price of its contribution. Without that death, those elements would still be locked away, trapped in a furnace that never sends anything back out. This is one of the stranger truths hiding beneath the surface of your own existence. You are, in a very literal sense, made of stellar wreckage. The iron in your blood, the calcium in your teeth, much of the oxygen you just breathed in, these were cooked inside a star that no longer exists. Some researchers describe this plainly. We are stardust, rearranged. It sounds gentle when phrased that way, but the actual event was catastrophic, chaotic, and completely indifferent to any future it might make possible. Whether every supernova produces elements in the same proportions is still an open question. Different models of these explosions predict slightly different mixes of heavy elements, and matching those predictions to what astronomers actually observe in old stars and gas clouds remains an active and unsettled area of study. The exact conditions inside a collapsing star, the exact timing of each nuclear reaction as the shockwave passes through, are still being refined through both observation and computer simulation. Nobody watched the very first supernovas happen. We reconstruct them from evidence left behind, and evidence has limits. There is also the deeper matter of timing. 4 heavy elements to end up in a planet like Earth. A first generation of massive stars needed to live fast and die early, seeding nearby gas clouds with new material. Then a second generation of stars needed to form from that enriched gas, slowly over long stretches of time. If the balance had tipped differently, if there had been too few early massive stars, or if their explosions had scattered material unevenly, the raw ingredients for rocky planets might never have gathered in one place. The chemistry that makes you possible depended on generations of dying stars happening in roughly the right order, in roughly the right amounts. If you had been present at one of those early supernovas, the light alone would have been enough to end you long before the shockwave arrived. And yet, at a much safer distance, spread across light years and cooled by time, that same violence became something else entirely. It became the material of rock and ocean and skin. The same event that would have destroyed you instantly, from close enough, is also the reason you exist at all, from far enough away and long enough after, we still do not fully understand every detail of how these deaths shaped the mix of elements now spread through the galaxy. We do not know exactly how many supernovas contributed to the specific cloud of gas that became our solar system. What seems clear is that stars had to die, over and over, long before anything alive could exist to wonder about it. Beneath the calm surface of the night sky lies that history of quiet, violent generosity. Sweet dreams do not usually dwell on exploding stars, but something like that had to happen first, before anything gentle could follow. Deep inside a dying star, something quietly strange happens. 3 helium nuclei, each one a small clump of 2 protons and 2 neutrons, collide in a narrow window of heat and pressure. If the timing is right, they fuse into a single nucleus of carbon. This process has a name, the triple alpha process, but the name matters less than the outcome. Without it, the universe would have almost no carbon at all, and without carbon, there would be no chains of chemistry long enough to build a cell, a leaf, or you. This fusion does not happen just anywhere. It happens in the core of a star that has already burned through its hydrogen, a star entering a later, hotter stage of its life. Gravity presses inward, temperature climbs past 100 million degrees. Helium nuclei that once drifted past each other now slam together with enough force to sometimes stick. It is a slow, rhythmic process, repeating over and over, across thousands of years, deep in a place no eye will ever see directly. You can picture it as a kind of breathing. A star swells, cools, contracts, and heats again, cycling through stages as it fuses lighter elements into heavier ones. Each cycle changes what the star is made of at its core. Hydrogen becomes helium, helium becomes carbon and oxygen. In the largest stars, the cycle continues further still, building neon, silicon, and eventually iron. Every step is a kind of exhale, releasing energy that holds the star up against its own weight. Carbon holds a peculiar importance in this sequence. It sits at a delicate midpoint. It forms just easily enough that stars produce it in real quantity, yet not so easily that it would have appeared in the universe's first moments. The early universe, cooling after the Big Bang, made almost nothing heavier than helium. Carbon had to wait. It had to wait for the first stars to live, age, and begin the fusion cycles inside their cores. Some researchers describe carbon's formation as almost too convenient. The nuclear physics involved requires a very specific energy match between the helium nuclei and the resulting carbon nucleus, a resonance that allows the reaction to proceed at the rate it does. If that resonance sat at a slightly different energy level, carbon would form far less often, and the universe you know would likely be sparse in the chemistry needed for anything like life. This observation has led some to view the coincidence as a sign that the physical constants of our universe seem tuned toward complexity. Others see it differently, suggesting that in a universe with many regions or many possible physical constants, we simply live in one of the versions where the numbers happen to work. Both views remain open. Neither can be tested directly yet. If you sat somehow near a star in this stage, though nothing living ever could, you would feel a slow pulse of heat pressing outward against gravity's pull inward. The light reaching you would carry the pale yellow and orange tones of a star working through its middle life, calm on the surface, turbulent within. Nothing about that light would tell you that carbon was quietly forming deep inside. One triple collision at a time. This carbon does not stay locked inside the star forever. Later, In the star's final stages, it gets carried outward and released into space, mixed into the gas and dust drifting between stars. That released material becomes part of the raw ingredients for future stars, future planets, and eventually, biology. Every carbon atom in your body traveled this path once. It formed in a stellar core, rode out into space during the star's later life, and drifted for an unknown length of time before becoming part of a cloud that would collapse into something new. The rhythm repeats across the universe, star after star, generation after generation. Some stars complete this cycle quickly, others take billions of years. The pace differs, but the pattern holds. Fusion, expansion, contraction, fusion again. Each stage building slightly heavier elements than the last. It is one of the universe's steadiest heartbeats, largely hidden, endlessly repeating. What remains open is why the physical conditions allowing this heartbeat exist at all, and why they align so closely with what complex chemistry requires. The equations describing nuclear resonance do not explain why the resonance sits where it does. They only describe what happens once it does. Somewhere in that gap between description and explanation lies a question still waiting for a clearer answer, one more quiet mystery folded into the deep cycles that made carbon, and eventually you, possible. Deep inside a dying star, something has to happen just right, or carbon never forms at all. Picture the core of a red giant, hot and dense, where helium nuclei drift and collide in the dark. 2 helium nuclei can fuse into beryllium, but that beryllium is unstable. It falls apart again, almost as fast as it forms, for carbon to appear. A 3rd helium nucleus has to strike that beryllium in the narrow instant before it decays. This is a close and constant near miss, repeated trillions of times. In every star, massive enough to try, the odds of that triple collision working at all would be vanishingly small, except for something strange in the physics. Carbon has an energy level, a specific internal state its nucleus can settle into, that sits almost exactly at the combined energy of beryllium and helium coming together. Physicists call this a resonance. It acts like a doorway that opens right where the reaction needs it to open. Without that resonance sitting in almost exactly the right place, the fusion would be too rare to matter, and stars would fill with helium and little else. The astronomer Fred Hoyle noticed this problem in the 1950s. He reasoned that since carbon clearly exists, and since it exists in enough abundance to build planets and people, there had to be an energy level in the carbon nucleus tuned to make the reaction likely. He predicted its existence before anyone had measured it. Laboratory experiments later confirmed a resonance, almost exactly where he said it should be. It remains one of the more striking predictions in the history of physics, made not from a direct measurement, but from the simple fact that carbon-based life was there to ask the question. This is where the mystery leans close to you personally. The precise placement of that energy level depends on the strength of the nuclear force and the strength of the electromagnetic force, 2 of the basic forces shaping the universe. If either force were even slightly different, the resonance would drift out of alignment. Some researchers have modeled what happens if you shift the strong nuclear force by a few percent in either direction. In many of those models, carbon production collapses. Stars would still shine. They would still die. But they would leave behind far less carbon, and possibly far less oxygen too, since oxygen forms from a similar near miss involving carbon and another helium nucleus. Not everyone agrees on how fragile this really is. Some physicists who have rerun Hoyle's numbers with more modern nuclear models find a wider range of safe values than first thought, suggesting carbon might survive somewhat larger shifts in the underlying forces. Others find the opposite, that the window is even narrower than Hoyle believed. The disagreement itself tells you something. This is still active, unsettled work, decades after the original prediction, and no one has produced a final, agreed answer for how easily this particular coincidence could have failed. If it had failed completely, the universe next door to this one, in some imagined variation, might be a quiet place. Stars would burn, galaxies would form. But carbon, the element that builds the backbone of every molecule in your body, would be a rare trace instead of a common one. There would likely be no coal, no petroleum, no long carbon chains twisting into proteins, or strands of anything resembling a genetic code. The universe would look almost the same from a distance, glowing with the same starlight, and yet be missing the one ingredient needed to become curious about itself. You can hold this thought quietly for a moment. Every carbon atom in your hands formed through this exact narrow doorway, inside a star that has likely since died, its outer layer scattered into space long before Earth existed. The resonance that made it possible sits at an energy level that did not have to land where it did. No one built it there on purpose, as far as anyone can show, and no experiment has revealed a hidden reason it must be exactly this way. It is simply the value nature settled on, and it happens to be the value that allows carbon to be common enough to matter. Some physicists set this coincidence beside the earlier puzzle of matter surviving annihilation, wondering if reality is layered with a series of narrow allowances, each one required for the last to matter at all. Others caution against reading too much meaning into a single resonance, noting that with enough universes or enough variations, some would inevitably land on values that work. Both views remain open. What stays certain is only this. Somewhere in a long-dead star, 3 helium nuclei found each other in the right instant, through a doorway tuned by numbers still not fully explained, and carbon began its long, quiet journey toward becoming you. The first stars in the universe lived fast and died in spectacular ways. They were made only from hydrogen and helium, the 2 simple elements left over from the early universe. No carbon, no oxygen, no iron, just the plainest ingredients possible, gathered into balls of gas and lit by gravity's pressure. These early stars are called population 3 stars. No one has ever seen one directly. Their existence rests on models, on the physics of how gas behaves under enormous gravity, and on faint, indirect evidence gathered from the oldest light we can detect. This is one of the extreme frontiers of the story. We are reasoning our way towards something that may have burned out over 13 billion years ago, using clues instead of direct sight. Picture one of these stars. Some models suggest they could have grown far larger than any star alive today, possibly hundreds of times the mass of our sun, without heavier elements to help gas cool and clump into smaller, more numerous stars. The raw material had fewer ways to break itself apart. It simply kept gathering, growing hotter and heavier until it became something the modern universe rarely allows. A star that massive would have burned through its fuel at a reckless pace. Where a star like the sun can shine steadily for 10 billion years, a population 3 giant might have lived for only a few million, in cosmic time that is barely a breath. Then it would have ended, likely in a violent collapse or a supernova so complete that some models predicted left nothing behind at all. No leftover core, no dense remnant, just an outward wave of newly made elements flung into the emptiness around it. This is the moment worth sitting with. That explosion, or that quiet collapse into nothing, scattered the first carbon, oxygen, and iron the universe had ever known. Before this, the space between stars held only hydrogen and helium, the same thin gas left from the Big Bang. After this, it held something new, heavier atoms, forged deep in a dying star, drifting outward to seed the space around it. You could think of it as the universe's first inheritance. A generation of stars that could not survive did not vanish without consequence. They left behind material for something else. Gas clouds enriched with new elements began to cool differently, clump differently, and form smaller, longer-lived stars. This second generation, called Population 2, is closer to what we still see in ancient star clusters today. Some competing models suggest the transition was not a single sharp break, but a gradual layering, with pockets of enrichment happening unevenly across different regions of the early universe. The exact pattern remains an open question, since we cannot directly observe those first several 100 million years in detail. If you had been present to witness one of these early deaths, and if your body could somehow have survived the radiation, you would have felt nothing like a solid shockwave. Space itself was still nearly empty. You would have simply watched a point of light unravel into shifting color, spreading outward in near total silence, the dark swallowing the glow within moments. What makes this stretch of history an extreme in its own right is the improbability stacked upon improbability. The imbalance between matter and antimatter had to survive first. Then gravity had to gather thin gas into stars against the odds of an expanding universe. Now those first unstable giants had to die in just the right way, at just the right pace, releasing new elements instead of collapsing into nothing useful. Some researchers wonder whether many of these early giants failed to enrich their surroundings at all, collapsing directly into black holes and taking their material with them into darkness. If too many did, the timeline for building future stars and planets would have stretched out far longer, or perhaps never happened the way it did. No one can yet say with confidence how common that failure was. The question is still open, sitting quietly in the gap between what our models predict and what the ancient universe actually did. What we do know is that somewhere in this uncertain stretch of time, enough of the first stars died the generous way. Enough heavy elements spread into the dark. Without that spreading, the raw material for rocky planets, oceans, and eventually you would not have existed at all. The universe took a chance on its own violence, and something usable came out the other side. Somewhere in a cold, dark cloud of gas and dust, about 4.5 billion years ago, something began to change. The cloud had been drifting quietly for a long time. It was mostly hydrogen, the simplest element, left over from the early universe. But mixed into that hydrogen was something else, something borrowed, something older. That cloud held atoms of carbon, oxygen, iron, and gold. These elements do not form in the early universe. They form inside stars, and they scatter into space only when those stars die. So before our sun could even begin to form, other stars had to live long lives and then end them. Their deaths seeded the cloud that would become our solar system. This is one of the quiet details that people rarely stop to picture. The sun is not made of primordial material. It is made of stellar ash. Every hydrogen atom, fusing in its core, right now sits next to atoms that were once part of other stars, stars that lived and burned and scattered themselves across the galaxy long before the sun existed. You could think of the cloud as a kind of graveyard, though a peaceful one, full of gentle drifting particles rather than anything solid or defined. For that cloud to become a star, gravity needed a nudge. Some researchers propose that a nearby supernova, the explosive death of a massive star, sent a shockwave through the cloud and caused it to begin collapsing. Others suggest the collapse could have started on its own, through slow gravitational instability, without any external trigger at all. Both ideas remain open. No one was there to see it, and the traces left behind are faint and hard to read with certainty. What we do know is that once collapse began, it did not happen evenly. The cloud fragmented into pockets, dense knots of gas pulling in on themselves. Most of those pockets probably formed other stars, siblings of the Sun that likely drifted away long ago, scattered by the slow tug of the galaxy's rotation. If you could see that early nursery today, you might see dozens of young stars glowing faintly together, each one built from the same drifting material, each one following its own quiet path outward into the dark. One knot of gas, slightly denser than its neighbors, kept collapsing. As it shrank, it spun faster, the way a skater spins faster when pulling their arms inward. This spin flattened the cloud into a disk, wide and thin, with the sun's seed glowing at the center. Around it, smaller clumps of dust and rock began to gather, the very beginning of planets. If you had drifted near that disk, you would have felt no wind and no sound, only a slow gravitational pull drawing you toward a growing, dim red light. The core of that central clump grew hotter as it grew denser. Eventually, it reached a temperature near 10 million degrees, hot enough for hydrogen atoms to fuse into helium. In that moment, a new star turned on. It was not sudden, not explosive. It was more like a candle catching flame after a long, slow warming. The sun had begun to shine, powered by the same nuclear process that still lights it today. Here is the detail worth sitting with. The sun's formation depended on earlier stars living and dying in just the right way, scattering just the right elements at just the right time, in just the right corner of the galaxy. If those earlier stars had never existed, the cloud would have stayed simple hydrogen and helium, unable to form rocky planets at all. Some models suggest that solar systems like ours may need at least 2 earlier generations of stars to have lived and died before enough heavy elements exist to build a planet like Earth. That number is still debated, and the timeline remains uncertain. There is also the quieter question of chance. The cloud that became the sun did not have to collapse where it did, or when it did. It did not have to sit near a supernova, if that is even what triggered it. It did not have to fragment in a way that left one not large enough to ignite, yet small enough to avoid becoming something far larger and shorter-lived, like the massive stars that burn fast and die young. None of this was guaranteed by any law of physics that we know. It followed the physics we understand, but the outcome was not fixed in advance. A slightly different push, a slightly different density, and the material that makes up your body might have ended up circling a colder star, or no star, adrift for a very long time. The sun's quiet, steady light is the product of stellar ash settling into balance. We still do not fully know how many similar clouds fail to do the same. Long before anyone understood carbon, or stars, or the slow chemistry that built a planet, people looked up and tried to place the Earth among the lights. The question was simple: where do we sit, and why is it warm enough to survive here? The answer took centuries, and it came from people who kept measuring the sky even when the numbers refused to make sense. In the 17th century, astronomers began timing the way planets moved. Johannes Kepler worked out that the planets travel in ellipses, not perfect circles, using only observations passed to him by another astronomer, Tycho Brahe. Kepler's numbers were exact but strange. He did not know why gravity should behave this way. He only knew that it did, and that the Earth held a particular kind of orbit, neither too close to the sun nor too far. That word, close, turns out to matter more than anyone realized at the time. A planet needs to sit inside a narrow band of distance from its star, a region sometimes called the habitable zone, where temperatures allow liquid water to exist on a surface. Too close, and water boils away into space. Too far, and it freezes into permanent ice. Earth happens to orbit near the middle of that band around the sun. Whether this is remarkable or common is still an open question, since astronomers have only recently gained the tools to check. For most of history, no one could see other planets around other stars at all. The first confirmed detection of a planet outside our solar system came only in 1992, orbiting a fast-spinning dead star called a pulsar. A few years later, in 1995, astronomers found a planet around a star like our Sun, using a technique that measures the small wobble a planet's gravity creates in its star's light. That wobble is tiny. Detecting it required instruments sensitive enough to notice a star trembling by a few meters per second, roughly walking pace, across trillions of kilometers of space. Since then, thousands of planets have turned up around other stars. Some sit inside their own habitable zones. None of them have been confirmed to hold life. The search continues, largely through space telescopes that watch for the small dimming of starlight when a planet crosses in front of its star, a method that works well, but still leaves enormous gaps in what we can actually see. Earth's own position looks, on paper, almost engineered for comfort. It sits close enough to the sun to stay warm, far enough to avoid scorching, and it holds an atmosphere thick enough to trap heat without smothering the surface entirely. One idea proposes that this is simply what happens sometimes, one outcome among countless failed arrangements elsewhere in the universe. And we exist here because this is the only place we could ask the question. A competing idea wonders whether rocky planets in survivable zones are far more common than early estimates suggested, meaning Earth may be less of an exception and more of a familiar pattern still waiting to be confirmed elsewhere. Neither view has settled the matter. The evidence is incomplete, and every year brings new planets that complicate the tally. What is not contested is how fragile the arrangement actually is. Slight shifts in Earth's distance from the sun, its tilt, or the thickness of its air would have left it barren. If you had formed on a planet drifting even a little closer to its star, your body would not exist to notice the heat, because no chemistry stable enough to build a body would have survived there at all. The same is true in the other direction, where cold alone would have kept water locked as ice forever, never becoming ocean, never becoming rain, never becoming anything alive. The astronomers who first mapped these orbits had no idea they were tracing the outer edge of a habitable window. They were solving equations, watching the sky return the same quiet answers, night after night. It took centuries of patient measurement before anyone understood that a planet's distance from its star was not just a number, but a boundary between existing and never existing at all. Earth crossed that boundary correctly, by whatever combination of chance and physics placed it there. The sun formed from the same collapsing cloud that birthed the planets, and Earth condensed from the leftover dust and rock circling nearby. It settled into an orbit that happened to be neither too near nor too far. No one designed that outcome. It emerged from the same drifting debris that could have easily produced a different arrangement entirely, one with no comfortable middle at all. Picture the young Earth, only about 60 million years old, glowing dull orange under a sky with no moon at all. It spins fast then, a day lasting maybe 6 hours, and the surface is still soft in places, still remembering the heat of its own formation. This is the world into which something enormous is about to arrive. Most people imagine the moon has always hung there, quiet and constant. But one widely supported idea, called the giant impact hypothesis, suggests something far stranger. A body roughly the size of Mars, which researchers sometimes call Theia, may have struck the young Earth at a grazing angle. The collision would have been unimaginable. Rock does not simply break in an impact like this. It vaporizes. It becomes a glowing cloud of melted stone and metal, flung into orbit around the wounded planet. If you had been floating nearby, watching, you would have seen the two worlds merge into one blinding smear of light, and then slowly, over months or years, watched that debris begin to gather itself into a ball. That ball became the moon. This is one explanation, and it remains the leading one, though it is not the only one on the table. Some researchers have proposed multiple smaller impacts instead of one giant blow. Others have modeled scenarios where the moon condenses from a disk of debris that behaves almost like a small, short-lived planet system of its own. The exact details of the strike, its angle, its speed, the size of Theia, are still argued over in careful computer simulations that do not all agree. What almost everyone in this field agrees on is stranger still. This collision, whichever form it took, may not have simply given Earth a nightlight. It may have made Earth livable at all. Consider what the moon actually does. Its gravity pulls on the oceans and creates tides, yes, but the deeper effect is on Earth's tilt. Earth spins on an axis tilted about 23 degrees, and the moon's steady gravitational pull helps hold that tilt roughly stable over long stretches of time. Without a large moon nearby, some models suggest Earth's tilt could wander unpredictably over millions of years, dragged around by the gravity of Jupiter and the other planets. A wildly wandering tilt would mean wild swings in climate, ice sweeping down to the equator in one age and blistering heat returning in another. Life, if it appeared at all under those conditions, might struggle to hold on long enough to become anything complex. This idea is called the stabilizing hypothesis, and it carries real weight, though it too has its skeptics. Some newer simulations suggest Earth's tilt might have stayed reasonably stable even without a large moon, depending on the exact configuration of the solar system. The question of just how essential the moon has been to Earth's long climate story remains genuinely open. What is not in question is that the moon exists, that it is unusually large compared to its home planet, and that its formation likely required a violent, low-probability event early in Earth's life. There is something quietly dizzying in that. The same collision that could have shattered Earth entirely, could have flung away its water, could have ended any chance of the story that followed, may have instead handed Earth the very thing that helped that story continue. A slightly different angle of impact, and Theia might have missed Earth altogether, or struck it dead center and destroyed both worlds. Neither outcome would have made you. You can think of this as one more narrow door in a long hallway of narrow doors. The matter that survived the early universe's near-total cancellation had to gather into stars. Those stars had to die to seed the galaxy with carbon and heavier atoms. A cloud of gas and dust had to collapse into a sun and a small rocky planet at just the right distance from it. And then, almost as an afterthought in cosmic terms, that planet had to survive a collision violent enough to reshape its whole surface and come out the other side with a moon that may have quietly stabilized its climate for billions of years afterward. None of this was guaranteed. None of it repeats itself in any predictable way elsewhere that we know of. Whether Theia truly existed, whether the moon truly stabilized Earth's tilt, whether some other rocky world somewhere else found a different, equally strange solution to the same problem. All of this remains under study, still debated, still incomplete. What can be said gently and with real wonder is that somewhere in that ancient chaos, a door opened rather than closed, and Earth kept moving toward becoming a place where something like you could eventually exist. Picture the young Earth, not long after the moon-forming collision settled into calm. The surface glows a dull orange, still too hot for oceans. Rock covers everything. There is no blue anywhere, no rain, no rivers. If you stood there, your body would not survive the heat, and there would be no air fit to breathe. The question that matters now is simple. Where did all the water come from? Earth formed too close to the sun to hold on to much water of its own. The inner solar system was a warm place in its early years, warm enough that light molecules like water vapor drifted outward instead of settling into the rock. Some water may have been trapped inside minerals as Earth formed, locked into crystal structures rather than pooled on the surface. But most researchers think that alone cannot account for the oceans we have now. Something had to arrive from farther out. The outer solar system, past the orbit of Mars, was cold enough for ice to form and stay. Comets carry that ice, dust, and frozen gas held together in bodies just a few miles wide, asteroids, especially a class called carbonaceous chondrites, carry water bound up in their minerals too. One long-standing idea is that Earth's oceans arrived this way, delivered slowly by comets and water-rich asteroids falling in from the cold dark beyond the frost line, the invisible boundary, past which ice can survive the sun's warmth. This idea has a problem, though, and it is a real one. When scientists measure the ratio of heavy hydrogen to ordinary hydrogen in comet ice, it often does not match the ratio found in Earth's ocean water. Different comets give different answers. Some match reasonably well. Others do not match at all. If comets were the main source, the chemical fingerprint should line up more consistently than it does. So attention has shifted toward asteroids instead, particularly those that formed farther out in the asteroid belt, in colder, wetter regions of the early disk of gas and dust that once surrounded the young sun. Meteorites from these bodies show a hydrogen ratio closer to what we find in seawater. Many researchers now think Earth's water arrived mostly through asteroid impacts rather than comet impacts, though comets likely contributed some. The exact mixture, the exact timeline, and the exact bodies involved remain open questions, with no full agreement yet. There is a gentler possibility sitting alongside these violent ones. Some water may have simply been present in the material Earth formed from, mixed into the dust grains that clumped together billions of years ago, never needing a later delivery at all. Under this view, the arriving comets and asteroids were topping off a supply that was partly already here, rather than creating it from nothing. No single model has settled which portion came from where. What makes this worth sitting with is the scale of coincidence hiding inside it. Earth needed to be close enough to the sun for liquid water to stay liquid rather than freeze or boil away, a narrow band scientists sometimes call the habitable zone. It also needed enough water delivered by whatever mix of comets, asteroids, and internal chemistry to fill oceans rather than leave a dry world glowing under an empty sky. Too little water, and there is no life as we understand it. Too much, and some models suggest a planet could drown its own continents. Jupiter likely played a quiet role in this arrangement too, its enormous gravity reaching across the solar system to fling icy bodies inward or fling them away entirely. Some researchers think Jupiter's position helped deliver water-rich material toward the inner planets during the solar system's early chaotic years. Others think Jupiter's gravity mostly cleared debris out, doing more harm than good to any delivery process. The balance between these effects is still debated, and simulations do not fully agree with one another. Beneath all of this sits the same quiet chain the whole story has been tracing, a distant planet's gravity nudging an icy body loose. That body drifting inward across empty space for millions of years. A collision, a scattering of ice and dust, a slow accumulation of something that would one day become rain, rivers and the ocean pressing gently against a shore. None of it was guaranteed. If the frost line had sat differently, if Jupiter had formed elsewhere, if the ratios of ice throughout the early disk had leaned another way, Earth might have stayed dry rock, circling a warm star, silent and empty, under a black sky. Instead, water found its way here, carried across the dark by bodies smaller than cities, and the question of exactly how still drifts, unresolved, above the surface of a calm and living sea. Picture the young Earth, just a few 100 million years old. There is no green anywhere, no blue ocean glinting under a friendly sun. The sky glows a dull orange, thick with gases that would choke you in seconds if you stood there and tried to breathe them in. This is the world water arrived on, and this is the world that had to change before anything like you could ever take shape. The air held almost no oxygen. Instead, it carried carbon dioxide, nitrogen, methane, and traces of hydrogen sulfide, and mixed closer to the inside of a volcano than to any breath you have ever taken. If you stood on that surface, your lungs would find nothing to use. Your skin would feel the weight of a thicker, heavier sky pressing down, one with far more pressure than the air around you tonight. There was no ozone layer yet, so ultraviolet light fell directly onto the rock and water below, raw and unfiltered, a kind of light no living cell could survive for long. And yet, something in that harsh mixture began to change. Lightning cracked across the methane-laden sky. Volcanic heat pulsed up from below. Ultraviolet light struck the churning gases again and again over millions of years, slowly. Some of the simple molecules in that atmosphere started rearranging themselves into more complicated ones, amino acids. The building blocks that would later assemble into proteins appear to have formed this way, adrift in ancient pools or drifting up from vents on the ocean floor. Scientists still argue over exactly where this chemistry took its first real steps. One long-standing idea points to shallow, sunlit pools on the surface, warmed by the sun and stirred by lightning, the so-called primordial soup, where simple molecules concentrated and reacted. A different idea points downward instead, toward deep-sea hydrothermal vents, cracks in the ocean floor, where mineral-rich water surges out at scalding temperatures, offering both heat and chemical gradients that could have powered early reactions without any sunlight at all. Both settings existed on early Earth. Which one, if either, actually hosted the first steps toward life remains an open question. And some researchers wonder if the true answer involves several places working in parallel rather than one single cradle. What makes this stretch of Earth's history so fragile is how narrow the chemistry had to be. Too much heat and fragile molecules break apart before they can link into anything useful. Too little energy, and nothing happens at all. The ingredients simply sit, inert, going nowhere. The mix of elements had to be just rich enough in carbon, hydrogen, nitrogen, and oxygen, arranged in just the right proportions, for chains of molecules to hold together long enough to do something new. Change even one of those variables by a wide margin, and this section of the story may never have moved forward. Liquid water made all of this possible. But water itself is a demanding host. It needed to stay liquid across enormous stretches of time, neither freezing solid nor boiling away into steam. Earth's distance from the sun placed it inside what researchers call the habitable zone, a band around a star where temperatures allow liquid water to persist on a planet's surface. This zone is not a guarantee of life, only a permission slip, a set of conditions that make certain kinds of chemistry possible, rather than certain kinds of chemistry inevitable. Mars sits near the edge of that same zone and shows signs of ancient rivers and lakes. Yet nothing we have found there suggests it ever crossed the threshold into biology. The early atmosphere itself was not fixed. It shifted as volcanic outgassing added new gases, as comets and asteroids delivered more water and organic material, and as chemical reactions slowly altered the mix overhead. This was not a single lucky moment, but a long unfolding process, one that took hundreds of millions of years to move from raw chemistry towards something that could copy itself. If you had watched from orbit across that entire span, you would have seen almost nothing change from one century to the next, and everything change across the whole stretch of deep time. No one has yet recreated, from start to finish, the exact sequence that turned simple molecules into a living cell. Laboratory experiments have produced amino acids and other organic building blocks under early Earth-like conditions, echoing real results first glimpsed in the famous Miller-Urey experiments decades ago. But the full bridge from those building blocks to true self-replicating life still has gaps no one has closed. The chemistry of early Earth remains a story with a plausible beginning, a plausible end, and a middle still waiting to be filled in. Picture the young Earth from far above, the way sunlight would have fallen on it 4 billion years ago. The light itself was the same light we know now, warm and golden, traveling the same 93 million miles from the same star. But what it touched down on was almost unrecognizable. Oceans covered most of the surface, dark and restless under a sky with no blue in it yet, or barely any. The air held little oxygen, so it would not have scattered sunlight the way it does today. The sky may have looked pale, or faintly orange, thick with haze from volcanic gases, and methane drifting up from a crust, still settling into itself. Under that strange light, nothing moved. No green covered the land, because there was no land worth covering, only islands of dark volcanic rock rising from the waves. No shapes swam beneath the surface. The light fell on water and stone, and fell again the next day, and the next for what may have been hundreds of millions of years, touching a world that had all the right ingredients for life, but none of the life itself yet. This is one of the quietest mysteries in the whole story of how you came to exist. Earth had liquid water. It had carbon, nitrogen, phosphorus, the raw elements that living things are built from. It had energy in sunlight and in heat leaking up through the ocean floor, and yet it took a very long time, by some estimates several 100 million years, for that ordinary chemistry to become something that could copy itself. Somewhere in that span, one single event happened that changed everything after it, and we still do not know how. Scientists call this event the origin of life, or abiogenesis, meaning life arising from non-living matter. The word sounds clinical, but the gap it describes is enormous. On one side sits a warm ocean full of drifting molecules bumping into each other in the dark, doing nothing in particular. On the other side sits a single cell, wrapped in a thin membrane, holding instructions inside itself, and able to make a copy of those instructions before it dies. Between those two states lies a boundary no laboratory has ever fully crossed, and no fossil has ever clearly recorded. Several ideas try to bridge it. One theory points to warm tidal pools on volcanic islands, where water evaporated in concentrated molecules over and over, giving chemistry countless attempts to stumble towards something self-copying. Another points to the deep ocean floor, to hydrothermal vents where mineral walls form tiny chambers, and where scientists wonder if those walls acted like an early, borrowed membrane before life had learned to build its own. A third idea suggests life did not begin on Earth at all, but arrived here already partly formed, riding inside comets or dust from space. A notion called panspermia. Each idea explains part of the puzzle. None of them explains all of it, and researchers openly disagree about which piece matters most. What makes this section belong to the story of light is this: every one of those early chemical experiments, whatever form they took, ran entirely on energy the sun was sending down for free. Sunlight striking shallow water, sunlight warming volcanic pools until they thickened and evaporated. Even at the vents, far from any sunlight at all, the energy driving the chemistry came from heat, another form of the same physics that lets light exist. Nothing about this process needed anything unusual from the universe. It only needed patience, and the right conditions held steady for long enough. If you had stood on that ancient shore, you would have felt an ordinary sun on your skin, and heard ordinary waves against ordinary rock. Nothing about the scene would have told you that inside some pool nearby, molecules were quietly rehearsing the first steps toward becoming you. There would have been no signal, no glow, no sign that anything was different about that particular puddle of water compared to 1,000 others nearby. That is part of what makes this moment so hard to study. It left no light of its own, no signature bright enough to survive 4 billion years of rock and pressure and time. We have the ocean it happened in. We have the chemistry it must have used. We do not have the moment itself, and we may never recover it. The long silence before the first cell remains, one of the deepest quiet places in your own history, lit by an ordinary sun and still unexplained. Somewhere in the deep past, the ocean nearly fell silent. Not the ocean of sound waves rolling through water, though that sound was there too, low and constant, the way it is now. This silence was quieter than that. It was the silence of species disappearing, one after another, until almost nothing was left to make a sound at all. The fossil record holds the memory of at least 5 great extinctions, moments when huge portions of life on Earth simply stopped. The worst of these happened around 252 million years ago, at the end of what scientists call the Permian period. Some researchers estimate that as much as 90% of ocean species vanished. The causes are still debated. One idea points to massive volcanic eruptions in what is now Siberia, pouring gas into the sky for thousands of years. Another idea focuses on the gas itself and how it may have warmed the oceans until they lost their oxygen. The exact chain of events remains an open question, pieced together from rock layers and chemical traces rather than any direct record. If you could have stood on the shore during that time, you might have heard very little. No bird song, since birds had not yet evolved. Perhaps wind over barren stone and waves against a shrinking coast. The sound of a planet thinning out. And yet something survived. That is the part of this story that deserves quiet attention. Every extinction, no matter how severe, left behind a few threads of life that kept going. Small, unremarkable creatures, often overlooked by size or grandeur, turned out to be the ones that made it through. Some ancient relatives of mammals endured the Permian collapse by living underground, sheltered from a world grown suddenly hostile above. The sound of that survival, if we could hear it, might have been almost too faint to notice. A slow heartbeat, a shallow breath in a burrow, life persisting not through strength, but through the accident of being small enough, or hidden enough, or lucky enough to avoid the worst of the change. There is a comparison worth sitting with here. Physicists studying the early universe describe a similar kind of near-total vanishing, though on a far larger scale. In the first fraction of a second after the Big Bang, matter and antimatter should have annihilated each other almost completely, leaving behind a universe of pure light, with nothing solid at all. Instead, one particle of matter survived for every billion pairs that cancelled out. That tiny surplus became everything you can see. The rest simply turned to radiation and dispersed into the dark. Life's extinctions work on a different scale, and for reasons that are at least partly understood. Unlike the antimatter puzzle, which remains unexplained by any accepted theory, but the pattern feels familiar. A near-total loss, a thin residue that continues. Whether at the scale of atoms or ecosystems, the universe seems to keep finding a way to leave just enough behind. Some paleontologists argue this pattern shows resilience built into life itself, a tendency towards survival that emerges from sheer variety. If enough forms of life exist, some will always find a way through, even the harshest event. Others are more cautious. They point out that survival often looks like luck rather than design. A burrow in the right place, a body small enough to need less food, a location far from the epicenter of the change. Whether resilience is a built-in property of living systems or simply the outcome of chance repeated many times remains genuinely unsettled. If you place your hand against your chest right now and feel your own heartbeat, you are feeling the end result of every one of those narrow survivals. Each extinction event removed branches from the tree of life, and yet the branch leading to you never broke. Not once, across hundreds of millions of years. It bent, it thinned, but it held. There is no full record of how many times this happened on smaller scales. Quiet die-offs never preserved in rock, entire lineages ending without a trace. The fossil record shows us only the events large enough to leave a mark. The smaller silences, the countless minor extinctions that shaped which creatures continued, are mostly lost to time. What we know for certain is incomplete, built from fragments, and full of gaps that may never close. Tonight, as you rest, think of that quiet burrow in the Permian dark, and the shallow breath inside it. Think of the one particle in a billion that did not vanish in the first instant of the universe. Both are echoes of the same soft, persistent fact. Something almost did not make it, and somehow it did. "66 million years ago, a rock about 10 kilometers wide crossed the orbit of Earth at the wrong moment. 10 kilometers sounds small against a planet 12,000 kilometers wide, but speed changes everything. That rock was moving near 20 kilometers per second, fast enough to cross a city in the time it takes you to blink. The numbers behind that collision are strange and almost beautiful, if you can hold both the beauty and the weight of it at once. 20 kilometers per second is roughly 70,000 kilometers per hour. At that speed, the object did not fall so much as arrive, releasing energy equal to billions of atomic bombs in a single instant, near what is now the coast of Mexico. The crater it left, called Chicxulub, still measures about 180 kilometers across, buried now under limestone and jungle and the slow patience of time. You can picture the orbit that carried it here as a long, silent ellipse, curving through the dark for millions of years before gravity and chance bent it toward this particular planet, at this particular angle, on this particular afternoon. Change the angle by a few degrees, and the rock might have skimmed past. Change the timing by an hour, and Earth's rotation would have carried this exact stretch of coastline out of the way. The asteroid did not need to be larger or faster to end an age. It only needed to be exactly where it was, exactly when it was. Before that day, dinosaurs had already ruled the planet for well over 100 million years. They were not fading, they were not failing. Many paleontologists described their populations at that moment as varied and widespread, filling forests and coastlines and floodplains around the globe. The asteroid did not finish a decline already underway, at least not by most current evidence. It simply arrived, and the mathematics of impact took over from there. Some researchers model the aftermath in stages almost like a slow, terrible clock. First, the fireball and shockwave, killing everything near the impact site within minutes. Then the dust and vaporized rock, lofted high enough to circle the planet, dimming sunlight for what some estimates place at a year or more. Photosynthesis slowed. Food chains starting with plants and plankton buckled, then broke, moving upward through the smaller creatures, and finally the large ones. About 3/4 of all species on Earth are thought to have vanished in the years that followed. If you had stood somewhere far from the impact site that day, you might have first noticed nothing at all, just a strange light on the horizon, hours before the true cold and dark arrived. The stakes of that single afternoon are difficult to hold in the mind at rest. Every branch of life still alive on Earth right now passed through that narrow, dim, uncertain window. Here is where the mathematics turns toward wonder rather than dread. Small mammals, mostly nocturnal, mostly modest in size, survived in numbers the larger animals did not. Some researchers think their small bodies needed less food during the lean years. Others point to burrowing habits, or a broader diet that let them eat almost anything available. No single explanation fully satisfies every case, and the debate about why some lineages survived while others vanished remains open among paleontologists today. What is not in question is the outcome. With the large dinosaurs gone, ecological space opened that had been closed for 100 million years. Mammals, previously confined to smaller niches, began to diversify. The line of primates that would eventually include you traces back through creatures that lived in that world of newly empty branches and unclaimed ground. Consider the ratio at the heart of it. One rock, roughly 10 kilometers across, arriving on one afternoon out of the 4.5 billion years Earth has existed. If you scaled Earth's whole history down to a single day, that impact would occupy less than half a second near the very end. And yet within that half second, an entire evolutionary path was cleared, one that eventually led, after another 66 million years of chance and change, to you. No one can say with certainty what Earth would look like today had that asteroid missed. Some researchers imagine dinosaurs continuing to evolve, perhaps even developing larger brains over deep time. Others think mammals might have found a different opening eventually, on a longer timeline. The question stays open, resting quietly at the edge of what fossils and models can tell us. What is certain is only this: the particular chain of life that produced you passed through a filter, measured in kilometers, seconds, and degrees of arc, numbers precise enough to calculate, and consequences too large to fully imagine. Long after the asteroid, long after the dust settled and the ferns returned, Earth kept testing the animals that survived. The planet's climate has never held still for very long. It swings slowly, like a pendulum with a period measured in tens of thousands of years. And more than once, that swing has come close to ending everything again. Picture the ice ages, one after another, glaciers creeping down across continents and then retreating, Some researchers point to a period called the Cryogenian, hundreds of millions of years before the dinosaurs, when the evidence suggests glaciers may have reached all the way to the equator. This is sometimes called Snowball Earth. If the whole planet froze over, from pole to pole, the question becomes how any life survived at all. One idea is that pockets of liquid water lingered near volcanic vents, or beneath thick ice where a little warmth leaked up from below. Another idea is that the freeze was never fully complete, that some open water remained near the equator, giving life a thin margin to hang on. The evidence is incomplete, and both pictures are still argued over today. Whichever version is closer to the truth, the planet eventually thawed, and it did so through its own slow chemistry. Volcanoes kept breathing carbon dioxide into the sky even while the ice locked away the oceans. Over long stretches of time, that gas built up, thickened the air, and began trapping heat again. The ice retreated. Life that had been pressed into a narrow, hidden refuge spread back out across a warming world. You can think of this as a planet regulating its own temperature, slowly, clumsily, without any intention at all, using nothing but rock and gas and time. That regulation depends on a balance so fine that small shifts in it have reshaped the entire history of life. The Earth sits at a distance from the Sun, where water can exist as liquid, rather than freezing solid or boiling away. A region sometimes called the habitable zone. Move the planet even a little closer or farther, and the story likely changes completely. The atmosphere itself is thin, a few dozen miles of breathable air pressed against a planet nearly 8,000 miles wide. If you could shrink Earth down to the size of an apple, the layer of air you depend on would be thinner than the apple's skin. That thin skin is the only thing standing between you and the vacuum above it, and it has been rebuilt, thinned, and thickened many times across deep history. More recent swings tell the same story on a shorter clock. Around 70,000 years ago, one line of genetic evidence suggests the human population may have dropped very low, though the exact cause and severity remain debated among researchers. Some have proposed a major volcanic eruption cooled the climate sharply around that time, straining early human groups already living close to the edge of survival. Other researchers are skeptical that any single eruption caused a global population crash, pointing instead to a mix of climate shifts, migration, and simple chance. No one has settled the argument. What is agreed on is that human history includes long stretches where our ancestors were few, scattered, and vulnerable to a climate that did not care whether they persisted. If you had been alive during one of those cold, dry stretches, your daily concern would not have been abstract. It would have been water, food, and warmth, found or lost by the width of a single bad season. The same unglamorous arithmetic: enough calories, enough shelter, enough luck, decided whether a small group of people left descendants at all. You are only here because, generation after generation, that arithmetic worked out. None of this required anything dramatic to go differently. Day, slightly colder, several centuries, a slightly drier stretch across the regions where early humans lived, a slightly less lucky set of harvests. Climate history is full of near misses that left no fossil, no scar, no obvious trace, because the populations that vanished left nothing behind to study. We only see the branches that made it through. The ones that didn't are simply absent, and there is no way to know how many there were. It is worth sitting with how ordinary these threats were. No asteroid, no supernova, nothing dramatic enough to leave a crater. Just slow shifts in temperature and rainfall, repeated often enough that eventually, somewhere, they mattered enough to end a lineage. Earth's climate has spent billions of years wandering between extremes, and life has spent that same time finding narrow paths through the wandering. Whether those paths were likely or lucky remains an open question, one that reaches quietly all the way down to you. Let's turn now from the sky to something smaller, something closer, something written inside every cell of your body. Somewhere in our deep past, the human family may have shrunk to a very small number. Some researchers who study ancient DNA believe our ancestors passed through periods when only a few thousand individuals, maybe even fewer, carried the entire future of our species forward. Think about that scale for a moment. Not millions, not even hundreds of thousands, a number small enough that a single hard winter, a single failed harvest of wild food could have ended everything. This idea comes from a strange kind of evidence. Scientists look at the genes of living people all over the world and notice something curious. Human genetic variation, the small differences that make each of us unique, is surprisingly limited. Compared to chimpanzees, our closest living relatives, humans show far less diversity in our DNA. A group of chimps living in one forest can carry more genetic difference among themselves than the entire human species carries across every continent. That pattern suggests a squeeze happened, a narrowing, a moment when the population dropped low enough that diversity got lost and never fully recovered. One theory points to a massive volcanic eruption that happened around 70,000 years ago in what is now Indonesia. The idea suggests this eruption threw so much ash and sulfur into the sky that it cooled the climate for years afterward, disrupting food sources across the regions where early humans lived. Some researchers have proposed this event nearly ended the human story before it truly began. It is a dramatic picture, a global winter brought on by a single mountain, but this theory remains contested, and that matters. Other scientists studying the same volcanic layers and the same ancient DNA argue the population dip may not connect to that eruption at all. The timing is uncertain. The genetic signals are hard to date precisely, and different methods of analysis sometimes point to different centuries, even different climate events entirely. Some researchers wonder if multiple smaller bottlenecks happened over long stretches of time, rather than one dramatic crisis. The question of exactly when and exactly why remains genuinely open. What everyone agrees on is this: the signal exists. Something happened to our ancestors that left a mark on the genes you carry right now, in every cell of your body, at this very moment. You are, in a very real sense, holding evidence of an ancient near-miss. The genetic narrowness in your DNA is not an accident of imagination. It is a measurable pattern, still being studied, still being argued over in scientific journals today. Picture, for a moment, small groups of early humans moving across a colder, harder version of Africa. Ash-grey skies, if the volcano theory holds. Thin, scattered bands of people spread far apart, each one holding a portion of what would become every person alive today. If you had been born into one of those groups, your survival would have depended on things you could never control. The luck of which valley had water, the luck of which season brought rain. None of it guaranteed. There is something worth sitting with here, gently, without alarm. Every ancestor in that thin chain of survivors had to live long enough to have a child, who also lived long enough to have a child across thousands of generations without a single break. One bottleneck survived does not guarantee the next one will be. And yet here you are, which means, so far, every single link held. Some scientists are now looking even further back, wondering whether other bottlenecks shaped earlier ancestors, Other close calls buried even deeper in our genetic history, moments so old that the evidence has nearly worn away. New techniques for reading ancient DNA are improving each year, and each new tool sometimes rewrites what came before. What counted as settled a decade ago is often revised today. The picture keeps shifting, which is part of what makes this such a lively area of study rather than a closed book. For now, the honest answer is that we do not know the full shape of our own bottleneck history. We know it happened in some form, more than once perhaps. We do not know every cause, every date, every population size with certainty. The evidence is incomplete, and researchers continue gathering more of it. One ancient bone, one ancient genome at a time. What remains certain is only this quiet, strange fact. Your existence required a very small number of people at some point to simply keep going. Somewhere in a warm valley in eastern Africa, perhaps 200,000 years ago, a small band of humans faced a season with too little water. We do not know their names, or their faces, or the exact shape of their days. We only know, from the patterns written into our shared genes, that very few of them lived to raise children who lived to raise more children. You are, in a very real sense, a message that made it through a narrow gap in time. Genetic studies suggest that human populations passed through several tight bottlenecks in our deep past. One especially striking piece of evidence points to a period when the number of breeding adults may have dropped to only a few thousand, maybe fewer. Some researchers link this to shifts in African climate, long droughts that turned open ground to dust and shrank the water holes that whole groups depended on. Other researchers are more cautious, noting that genetic signals like this can also arise from ordinary population movements or from limits in how well we can read the deep past from the DNA of people alive today. The evidence is incomplete, and the exact cause of that squeeze remains an open question. What is not in question is how strange it feels to sit with the outcome. A drought that lowered a water table by some unknowable amount could have ended everything that would ever call itself human. There was no plan protecting our ancestors, no guarantee written into the world that a thinking species would eventually appear here. There was only weather, luck, and whichever small groups happened to find enough food near enough water in the right years. If you traced your family back far enough, past every name in every record, you would eventually arrive at people who did not know they were saving anything. They were only trying to get through another dry season alive. Around 70,000 years ago, a massive volcanic eruption on the island now called Sumatra sent ash and sulfur gas into the upper atmosphere, and some scientists have proposed that the resulting cooling may have placed further strain on human populations already living close to the edge. Ice cores and sediment layers show the eruption happened. What effect it had on human numbers is debated, and some researchers question whether it caused a population crash at all, or whether other pressures were already at work. Either way, the timing sits uncomfortably close to other signs of a demographic squeeze, and no one has fully resolved how these threads connect. It is worth pausing on what a bottleneck like this actually does. When a population shrinks that far, most of the genetic variety that existed before is lost with the people who did not survive. The humans who came after inherited a narrower set of genes than their ancestors carried only a few thousand years earlier. In a way, every person alive today descends from survivors of survivors, a lineage thinned again and again by events none of them could have predicted or prevented. If you stood in that valley during the worst of it, the sky would look ordinary, the heat would feel unremarkable, and nothing about the moment would announce itself as a hinge in the story of a species. Other bottlenecks may have happened earlier still, some researchers argue, pointing to genetic patterns that suggest an even older squeeze, perhaps linked to shifting ice ages or changing coastlines that split small groups apart. These claims remain contested, resting on statistical models of DNA rather than direct fossil counts, and different teams reach different numbers depending on their assumptions. The honest answer is that we do not have a clean, agreed-upon history of exactly how many times our ancestors nearly disappeared. We only have scattered signs layered across genomes and rock, hinting that it happened more than once. What stays constant through all of this uncertainty is the shape of the pattern. Small groups, harsh stretches of climate, a thinning of the family tree that left survivors carrying the whole of what would become humanity forward. None of them were choosing to become ancestors. They were simply living, adapting, failing, and sometimes just barely enduring long enough for the next generation to exist at all. The chain never broke, though it came close enough that a colder decade, a drier valley, or a different eruption could plausibly have ended it. You are the end of a thread that thinned almost to nothing more than once, for reasons still not fully understood and still somehow held. Let your mind drift back now, past every step we have walked together tonight, all the way to the very first light. Before stars, before atoms even had a place to sit still, there was only a hot, bright fog of particles, and inside that fog, a tiny imbalance that should not have been enough to matter. One extra particle of matter for every billion pairs that cancelled out. That whisper of asymmetry is the first link in a chain that somehow reaches all the way to you, lying here now, breathing slowly in the dark. Follow the chain forward. That faint excess of matter cooled into hydrogen and helium, drifting as thin gas through an expanding dark. Gravity, patient and unglamorous, pulled that gas into clumps. The clumps became clouds. The clouds became stars, and the stars began to burn. Inside those first stars, simple elements fused into heavier ones. When the largest of those stars ran out of fuel, they did not fade quietly. They collapsed and then exploded, scattering carbon, oxygen, calcium, and iron across the space between other stars. None of this had to happen in any particular way. The clumping could have been slower. The explosions could have scattered their elements too thin, or too far, or not at all. A new generation of stars formed from that scattered debris, our own sun among them, around the sun. A disk of leftover dust and rock slowly gathered itself into planets. One of those planets settled into a narrow band of warmth, not too close to the sun, not too far, where water could stay liquid instead of freezing solid or boiling away. A moon-forming collision, sometime in that planet's early violence, gave it a stabilizing companion in the sky. Comets and asteroids, wandering in from the cold outer dark, may have delivered water to a surface that started out dry. Every one of these events had a version where it simply did not happen, or happened differently, and the planet stayed empty. On that planet, chemistry slowly became biology in a process still not fully understood. A single cell learned to copy itself. Billions of years passed, most of them spent unremarkably. One cell becoming many, many becoming complex, complex becoming strange and varied. Nearly every branch of that unfolding tree of life met an ending. Ice ages came and went. An asteroid struck a peninsula and ended the age of dinosaurs, opening space for small mammals to spread and diversify. Your own ancestors passed through population bottlenecks so narrow that entire lineages could have blinked out with a change in the weather. Each of these moments is its own small mystery, still debated, still incomplete, and each one had to resolve in your favor or you would not be here to wonder about any of it. Here is the strange part, to sit with every element inside your body. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, was made inside a star that died before the sun was even born. You are not simply living near the stars. You are built from their leftover material. The atoms in your hand are older than the sun, older than the earth, forged in a furnace that stopped burning long before either one existed. If you traced any single atom in your body backward far enough, its story would end inside a star that no longer exists, in a galaxy that may no longer exist in the same shape. And all of it, every star, every atom, every quiet chain of chances that led to this exact moment, depends on that first small asymmetry, the one extra matter particle in a billion, that physics still cannot fully explain. Take that asymmetry away, and none of the rest of the chain even begins. No stars to make the calcium, no planets to hold the water. No moment where cooling chemistry became something that could remember and wonder. Some researchers hold on to the hope that new experiments, more sensitive than anything built before, will finally catch the small bias in nature that tipped the balance. Others wonder if the true explanation lies somewhere our current models cannot yet reach at all. Both possibilities remain open tonight, exactly as open as they were before you started listening. You are, in the most literal sense available to physics, the improbable residue of an almost perfect cancellation, dressed up in stardust and given billions of years to become curious about itself. Rest in that thought a while longer. There is nowhere else you need to be. Picture the Earth now turning slowly in the dark, one half leaning into sunlight, the other resting in shadow. Clouds drift over blue water. Somewhere down there, a room is quiet. A body lies still, under warm blankets, breathing slow. And that body is made of atoms that should not have survived the first second of time. That body is you. We have spent this long night following one thread. The early universe should have made matter and antimatter in equal amounts, and they should have met and turned entirely into light, leaving nothing solid behind. No stars, no planets, no oceans, no ears to hear these words. Instead, for every billion pairs that vanished into radiation, one lonely particle of matter was left standing. From that tiny surplus came hydrogen and helium, and eventually every heavier thing the stars would learn to build. From that surplus came you. We still do not know why that surplus exists. Physicists call the search for its cause baryogenesis, and decades of careful work in particle accelerators have found hints of the kind of imbalance needed, called CP violation, but never enough of it to explain the universe we actually see. Some researchers wonder if new particles, still undiscovered, tipped the early scales. Others wonder if the answer lies in conditions no accelerator on Earth can reach. Moments after the Big Bang, too extreme to recreate. Both ideas remain open. Neither has won, and so every atom in your hand carries an unsolved question inside it. The carbon in your blood was cooked inside a dying star, through a nuclear coincidence so narrow that if the numbers had been slightly different, carbon would barely exist at all. The oxygen you just breathed in came from another dying star, flung outward long before the sun was even born. The water resting in the glass by your bed may have arrived on icy visitors from the far, cold edges of the solar system, delivered here across billions of years of empty space. None of this had to happen in the order it did, and yet, somehow it did. Think of the long chain behind you now, stretching back through nights like this one, back through ancestors who survived cold seasons and narrow escapes, back through the first simple cells that held on through errors when almost everything else was erased. Think of the asteroid that could have ended a different story instead of allowing yours to continue. Think of the moon above you now, formed from a violent collision that also gently calmed the tilt of the earth and made its seasons mild enough for slow, patient life to take root. Every one of those events could have gone differently. None of them were guaranteed. You do not need to hold all of this awake in your mind. You do not need to solve it tonight, or any night. The universe has been asking these questions of itself for over 13 billion years, and it has not finished answering them yet. It may take a lifetime, or many lifetimes, to understand why matter won out over its own mirror image. It may never be answered at all, and still, here you are, breathing in the dark, made of the leftover residue of that ancient, near-perfect cancellation. Let that be enough for tonight. Not an answer, but a quiet kind of proof, resting in your own chest with every breath. Somewhere above you, galaxies are turning slowly, the way they always have, indifferent and patient and vast. Somewhere below you, the earth keeps spinning without asking anyone's permission. The ocean keeps resting under whatever moonlight reaches it tonight. And you, improbable and small and entirely real, get to rest along with it. You do not have to understand the universe to belong inside it. You already do. The same forces that shaped starlight shaped the calcium in your bones. The same slow cooling that let atoms form is what allows your body right now to soften into sleep. You are not separate from any of this. You are what happens when the universe, against long odds, decides to stay. So let your breathing slow. Let your shoulders settle into the mattress, somewhere out past the ceiling, past the atmosphere, past the reach of any telescope we have built. The same quiet question keeps turning in the dark, unfinished and unafraid of staying that way. You do not need to finish it either. You only need to rest inside it, the way you have all along, without ever quite noticing. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.